All right, today we're going to take a look at section 8.5, which is partial fractions. And the crux of what we're doing in this section is algebra. I know we keep doing that a lot, don't we? Like the whole premise is something about algebra or trig, and then we show how to use it in calculus. That's what we've been doing this whole chapter pretty much, hasn't it been? So this actually is a college algebra concept. But I will tell you that most of the time, college algebra classes don't actually teach this. It's one of those end topic kind of things that are perfectly valid for college algebra to teach, but they're not useful so much until you get to calculus 2. So it's one of the things that often get left out of the discussion. The whole premise of this section is that when you have a fraction that looks like this, as you know from A plus B over C, that's what I've written down. As you know from working with your basic skills quiz, this showed up, and from working in section 8.1, this showed up, that sometimes it is helpful to rewrite this as each of the individual pieces over that denominator, right? That's the basic idea of what's going on in this section. The difference is that sometimes the section actually starts out, or the problem actually starts out looking something like this, and it doesn't look like there's anything on top to be able to actually separate into two fractions. So the algebra that we're going to do is going to be taking that thing that looks like a single value on top and somehow separating it out and to create two fractions that don't sort of look like they're there already. That's the basic idea, okay? So let's actually take a look. This is one of those sections where I think it's good to sort of write down a step-by-step procedure of what we're going to do. So what we're going to be doing is we're going to be taking a fraction that looks like n of x numerator over d of x denominator, and we're going to be decomposing it, not like in chemistry or biology, but decomposing it, breaking it down for mathematics. So the first thing we're going to do is if that numerator degree is larger, we're going to divide it, larger or equal. But you guys knew that anyway. We've already done that with long division stuff, so that's not really a new step. It's just a reminder that that happens. The second issue, and sometimes the first issue just won't happen, right? It says if the degree happens. The second thing we're going to do is we're going to factor the denominator. Okay. The third thing we're going to do is we're going to write the denominator as a summation of fractions with each factor as a separate denominator. So let me just kind of briefly write down what that means in terms of an example. So for instance, if I were able to factor my denominator into x plus 3, x minus 3, well, that doesn't look very good, but I would separate this into two fractions, one with a denominator x plus 3 and the other with a denominator x minus 3. Notice there's no numerators written in yet, but that's just separating those into two potential fractions. Step 4 is to write each numerator with a degree 1 less than the denominator. So if I were still working with that example that I wrote in red right there, what is the degree of each of those new denominators that I have written on the right-hand side? What's the degree of x plus 3 and x minus 3? It's a degree of 1, right? So if I'm going to write the numerator with a degree 1 less than 1, that means the numerator has a degree of 0. What values, or what does something look like if it has a degree of 0? Like a 1 or just some kind of a constant, right? So if I had the number 5, that would be degree 0. So these numbers on top would be some kind of a single number here. And I'll show you as we work a problem how that actually plays out. But that's what's going to end up happening on those, is the degree is going to be 1 less when we write that down. Step 5 is actually reconciling the summation with the original fraction. And again, I'm not going to show you a detail of this now, but basically what it means is we're going to multiply the two fractions back together. So we did all that work to get them to all be single, and we're going to sort of consolidate them back in together, and I'll show you why that's helpful. And then my note here, I already mentioned once before, partial fractions is a college algebra topic not typically covered in college algebra for lack of time. So we're going to cover it here. The concept of actually doing it is the part that's algebra, and then once we actually get these things separated out, we'll use our calculus skills that we already have to be able to do that. So there's nothing new calculus today in this section. It's all just college algebra concept. Okay? All right, so let's take a look at an example. We have a fraction here that's 1 over 4x squared minus 1. And the first step in that decomposition business on the previous slide was this idea that if the degree of the numerator is larger, we use long division. Do we need that on this problem? No, we don't need that on this problem. So we're automatically starting on this problem on step 2. So step 2 says, what should I do? Factor. So I need to factor that denominator. So how will this denominator factor? Right. It's actually a difference of squares, right? So all I've done is factor the denominator. And it's true that I could write this now as 1 over 2x plus 1 times 1 over 2x minus 1. But that's not what partial fractions is helpful for. Partial fractions is helpful for writing them as a summation, that is, two fractions added together, not multiplied together. All right, so what does step 3 say I'm supposed to do? Look up there. What's it say? All right. So the next step I'm supposed to do is I'm supposed to, in fact, what I'm going to stop here, I'm going to pause the moment. No, I'll do it in a minute. Let me leave it right here for now. Okay, so step 3 says I'm going to write this as a summation of two fractions with those individual denominators, right? That's what I showed you on the previous slide in red. What's the degree of the numerator of each of these numerators? It's going to be a degree, well, the degree of the denominator is 1. What's the degree of the numerator going to be? 0, which means the numerators are actually going to be just constants, right? They could be a 1, or they could be a 6, or they could be a 1/2. I don't know what number they're going to be, but they're going to be some constant number. I'm going to represent a constant with a letter, and the letters we're going to use are A and B. And for whatever reason, those seem to be the typical letters, the things that show up as this. You're going to see capital letters used as we do partial fractions, and they're going to go in alphabetical order. So if I had 3 separate fractions or a need for 3 different letters, I'd use A, B, and C. That's just standard for this particular topic. All right, so then what? Well, I'm going to pause right here on this problem, and we'll come back once we figure out what in the world A and B are. Because if I know what A and B are here, I can do this problem. I'm going to use a little bit of substitution. I mean, all I've got are numbers on top. And I've got this 2x plus 1, 2x minus 1 on bottom, which means my antiderivative is going to involve some logs, right? So I've got a little bit of substitution, a little bit of logs. But the integration for this particular piece isn't really a big deal if I can figure out what in the world A and B have to be. Is everybody good with that? So the question then becomes, well, how do I figure out what A and B has to be? That's what step 4 was all about on the previous slide. What does step 4 say I needed to do? Oh, then it's step 5. Let's try again. Reconcile, that's the step I wanted. So step 5, this idea of reconciling these two values together. Okay, so over here on the side that I've sort of drawn this line down the middle, I'm going to work a little bit of algebra over here on the right-hand side, on your right-hand side. And as I'm doing that, what I'm going to do is I'm going to take these two separate fractions that I've created with this sort of weird A and B in the numerator, and I'm going to multiply them back together. So if I multiply these two fractions back together, I get the same denominator that I originally had, 2x plus 1 times 2x minus 1, right? Well, what happens to the numerators? What will the first numerator that was originally now A become? What was that? Not yet. You haven't heard quite the right idea yet.
Is it A times 2x minus 1?
Yes. So one of the features, I'll use it in red over here to recognize, when I'm trying to combine fractions together that are added, I have to have what? A common denominator, which means that the first fraction here would then be multiplied by 2x minus 1, and the second fraction would be multiplied by 2x plus 1. Is everybody with me on that? So that first numerator, which was originally A, it now becomes A times 2x minus 1. And the second numerator, which was originally B, is now B times 2x plus 1. So it looks like I've done something that's sort of circular reasoning. I separated something so that I can multiply it back together. What in the world did I do that for? Well, it's going to allow us to find out what A and B are. That's why. So let's go ahead and distribute and clean everything up in that numerator then. If I multiply everything out, what does that numerator become? So I'm going to call this n of x as my numerator because it's the only piece that I really need to keep working with. What does that numerator become? Somebody multiply for me, please. Okay, so I'm going to put the 2 and the A and then the X like that, just for alphabetical order. Is that okay, Kirsten? Okay. And then what's next? You started for me, Kirsten. Can you keep going?
Plus 2bx.
First minus my A, and then plus 2bx. And then plus b. That's the numerator of this particular fraction. But what is that numerator supposed to be equal to? It's supposed to be equal to 1. Why? Because my original fraction had the exact same denominator that this new fraction, 2x plus 1, 2x minus 1 is. And the original numerator is 1. So this new numerator has to also be equal to 1 in some way. Right? These two fractions are supposed to be the same thing, just in a different form, which means that the denominators, they already match. The numerators must match as well. So this numerator that we've just created is actually equal to 1. So 2ax minus a plus 2bx plus b equals 1. So what we're going to do is we're going to isolate the two pieces. There are two different kinds of values in that expression. There's values that are multiplied by x, and then there's values that don't have an x in them, right? That are the constants here. So I'm going to sort of write down that I've got x values or x terms, and I've got constant terms. Or, you know what, I'll write it this way. I've got terms that are numbers. Numbers only. So what terms have an x in them? The 2ax and the 2bx. So they have values 2a and 2b that are each multiplied by x. So I've sort of like factored that x out. You can think about it that way. And the numbered terms, the terms that don't have an x in them, are what? Negative a and positive b. Okay, now look back at the term again. This is all supposed to equal the number 1. So how many x's is it supposed to equal? How many x's are in my original numerator? 0. There are 0 x's up here, right? There are no x's. That's equivalent to having 0x. If it helps you to see that, you can write that. This numerator is actually 0x plus 1. So the terms that have an x in them have to add up to 0. They have to go away because I should not have any terms with x in it. The terms that are constant terms have to add up to the number 1. At this point, do you know what we have? We have a wonderful college algebra topic that I know you've all done before.
You add those together.
We have a system of equations with two variables, a and b. So two equations, two variables, which means I can solve for what I've got. This is algebra. In fact, it's before college algebra. It's usually introduced in intermediate algebra, algebra 2 in high school. So you can do one of two things, are the most popular anyway. You can do substitution, where you solve one equation for one variable and plug it into the other one. Or you can do elimination, or sometimes called the addition method, where you line them up and get something to add up to 0. And either method is perfectly fine to use. Which one would you like to use? Okay, I heard some substitutions. So if we want to use substitution, what do you want to do what do you want to solve? Let's pick an equation you want to solve for. You want to solve using the first equation and the second equation. First one. All right. So if I take my first equation, do you want to solve for a or b? A. It really doesn't make any difference, so let's just pick one, right? A. So if I solve this for a, then I find out that 2a equals negative 2b, which means that a equals negative b. So far, so good? What do I do with that next? I plug negative b into the other equation. You got it. So that's the substitution method. So then I take my second equation. I replace the a with negative b. So right now it's negative times negative b plus 2b equals 0. Sorry, 1. My green's not quite dark enough to read over there on that edge. It's not 2b. Oh no. I was looking at the line above. I'm sorry. We'll fix it. Plus b equals 1. Oh, good, because now I'm still on the green, or on the brown. All right, so what's negative negative b plus b? That's 2b. So if 2b equals 1, what does b equal? 1/2. So b is 1/2. So what's a? Negative 1/2, right? We solved for a and b. So back over here in my original problem, which we were working on, which we wanted. I mean, we want them separated out, make no mistake. But we have to push them back together to reconcile them to find out what the a and the b are. So my a is negative 1/2 over the 2x plus 1. My b is positive 1/2 over the 2x minus 1 dx. Okay, everybody good with that? Because the calculus for doing this is not difficult. Let me move to the next slide to finish the calculus. All right, so we'll take it in a couple of smaller steps. A couple features. We mentioned earlier already, or I mentioned earlier, that there's going to be some u substitution because you've got denominators that don't just have a single variable in them. The other thing that you're going to have here is you're going to have two separate u substitutions because the denominators aren't the same. So the first thing I would like to do is I would actually like to separate these into two separate pieces. Everybody good with that? Second thing I'd like to do is I'm not a fan of having the numerator have a fraction in it. That sort of feels weird to me. I don't like it very much. So I'm going to write mine with the number out in front. You can choose to leave it there if it does not bother you, of course, but I don't know, I'm a little OCD like that, so I'll just pull it out. All right, so on the first one, let's do the first one and we'll kind of finish it through and then we'll come back for the second piece. What is the first u going to be in my first u substitution? Right. 2x plus 1. What is my du going to be? 2 dx. And I don't have a 2 in there, so I'm going to have to put it over 2, right? So I already had a 1/2 in the problem, negative 1/2. I'm now going to have another 1/2 from the du piece, and then I'm going to have 1 over u du. Does everybody understand why I have two 1/2s? Okay? All right, so what's the antiderivative going to work out to being over here then? Right, natural log of absolute value of u. I've got a negative 1/4 in front. And I can put this back together and say this is negative 1/4 natural log of 2x plus 1. Any questions on that piece? Okay, just to keep it clear and clarified, I'm not going to call the other one u because I already used u. I'm going to use something else. I'm going to use t. Whenever I use t, I'm really careful to put that little curly on the bottom of it. I don't want it to look like a plus sign. If you don't want to use t, use w or something like that. That'll work as well. So I'm going to use t. And if I use t, then what is my t substitution here going to be? Right, 2x minus 1. So dt is going to be 2 dt. Yeah, 2 dx. Get the right letter in there. And I'm going to have to do the division by 2, just like I did on the other piece. So I end up with plus the 1/2, and then I have another 1/2 from the dx and then dt. I've got an integral of 1 over t dt. So my antiderivative is going to give me 1/4, and then what? Natural log of the absolute value of t plus my constant. And then plugging back in the value for t, this is plus the natural log of 2x minus 1 plus my c. There's two small pieces of cleanup I can do to consolidate this. Any thoughts? Pull out a 1/4, that's one issue. So if I pull out a 1/4, do I have space? I do. Okay, so I'm going to pull out the 1/4. As I pull out the 1/4, I'm going to actually put them with the second piece, that is this piece, first, so that the addition comes before the subtraction. And you'll see why that sort of helps us in terms of thinking about it here in just a second. But so this is natural log of 2x minus 1, and then minus the natural log of 2x plus 1. Absolute value of that, and then plus c. There's one more thing I can do.
You combine the natural logs.
I can combine the natural logs. Currently, the natural logs are subtracted, so how do we combine the natural logs? With division of what's inside of them. That's a log property. I know it's been like 2 months probably since we've seen that, but the property says that I can actually do this as natural log then. We can still keep the absolute values. We can put the absolute values either individually in the numerator and denominator or around the whole thing is fine too. So this is 2x minus 1 on top and 2x plus 1 on bottom. There's a single log expression when we're done. Okay, you guys remember that log property now? I know it's been a little while since we did that, but we did do that earlier. Any questions on this one? Okay, the calculus was not hard, right? But the beginning part with the algebra is a little different. Okay, let's do another one of these. I put this one in as the second problem. It looks more complicated because there's more stuff on top, doesn't it? But it's actually a little bit cleaner to work through parts of this than the other one was. All right, so the first part of my steps of what I should do talk about this degree of the numerator, degree of the denominator. Does it apply in this case? No, it doesn't. Why not? Yeah, the numerator degree is still smaller than the denominator degree, so I don't have to do that. So what does step 2 say I should do with this problem? I should factor. So the numerator stays the same, nothing happens there. But my denominator factors. What does my denominator factor into? Thank you. X squared times x plus 1. And there's a trick. This is why this is the second example. So normally now we would write that this is the addition of two different denominator fractions, right? But this one actually has the possibility that it could be 3 of them. You see, if I had any of those 3 particular denominators and I multiplied them back together, I'd still get the original denominator I started with, right? So anytime you've got a duplicate or a double zero like this, like a double fraction, your denominator will actually separate into 2 different possibilities. One of them that actually is x squared, but one of them that's actually what that factor of that would be as well, namely x in this case. That's a little weird. All right, so this is my, oops, it's back in black. This is my partial fraction I'm going to be working with. Now, here's something different. That middle term has a degree of what in the numerator or in the denominator? A 2. Well, I didn't show you what to do with a degree 2. We've only done degree 1s, right? So the degree 1s start out the same. I'm going to have an a right here, and I'm going to have a constant on the second one as well, but I'm going to wait to hold off on the b just so that the r's all match. Above the x squared, we're going to write bx plus c, and then above the last one, we're going to write d, and let me explain. All right, so for starters, middle fraction, the degree of that numerator is 1 less than the degree of the denominator, right? And it is the most vague or broad way that I could write that numerator to fit that description. It's a linear equation where it has one component that has an x in it and one component that has the constant in it. Does that make sense? So anytime you have a power 2 in the denominator, you're going to have a linear, like mx plus b, above it. That's what's always going to happen. But as you can see, that sort of makes this look weird, because if I'm going to now reconcile these back together, I have 3 fractions to reconcile, don't I? So we have to think about what happens as we work through the algebra on this. So I'm going to pause on the calculus, and we're going to work on our algebra. So the algebra part of this, I'm not going to have space on the side like I did in the last problem. It's going to have the x squared times x plus 1 as the denominator. What in the world do I have to multiply that first fraction a over x by in order to get that denominator to become x squared times x plus 1? 1x and the x plus 1. So this numerator becomes ax squared plus ax. Does that make sense? Okay. What about the second one?
X plus 1.
I only have to multiply this one by x plus 1. Well, that's good. But notice when I multiply by x plus 1 to the numerator, which was bx plus c, what in the world do I get there? Okay, you know what? Let me pause something with you, because, yeah, I overcomplicated something. I'll explain, but let me erase it and then we'll do it, okay? The overcomplication was on that bx plus c. Hang on. Look at that, you just disappear everything. Okay, let's go back up to here. I'm sorry. There is one nuance to doing this. What I said before is correct, that when you have the denominator that's a power, that you write it with the degree 1 less. That is a correct statement. However, because this is a duplicate factor where we've got the x here and the x squared there, if I do the bx plus c, it will work. It will overcomplicate the problem. I'm going to show you one where we need the bx plus c, but for the moment, b will work here, and it will leave the problem as simple as it can be as we're working. So the only reason I'm allowed to put the b here is because this denominator is simply a multiple of the other denominator. It's because of this double zero thing. I had forgotten about that. I'm so sorry. But what we would have done would work. It just would have been really a lot more work than we needed. So let's use the b here. I've got the c already over here. And I'll show you an example. The third example has a case where we're going to have that linear factor in the numerator. Okay, so as we said before, this is going to be times x plus 1. So my denominator has that x squared times x plus 1 denominator. And then the first numerator is going to become what then? What did we say? ax squared plus ax. Okay. The middle one, you guys already told me we're only going to multiply by x plus 1 on that one, right? So I can get away with, on this one, only having bx plus b. What about the third one? What does it need to be multiplied by? X squared. So it becomes cx squared. That whole numerator, however, this time does not equal 1. It equals a variety of things, right? It has three different individual add-ins in that numerator that this is supposed to be equal to. It's supposed to be equal on top to 4x squared plus 2x minus 1. So what we're going to do is we're going to collect like terms, just like we did before. So the first terms that are alike are the terms that have values of x squared in them. There are two on the left. There's an ax squared and a cx squared. And there's one on the right. It's a 4x squared. So if I'm collecting x squared terms, I have on the left a plus c, and it equals the number 4 on the right. Does that make sense to everyone? Sort of like I've factored the x squared out of all of them. There has to be the same number of x squared on the left of the equation as there is on the right of the equation. We're going to do the same thing then with the x terms. So my x terms. Okay, so what do we have on the left-hand side? A plus b, and then this is going to equal 2. Good. And then I've got my numbers or my constants. So you can, I'm going to put number in here. What do I have in terms of the constants? I only have one constant, and that's awfully friendly. What does that constant then equal? -1, and this is the best part of this problem, is that you already know what b equals, which means you can actually back substitute without doing a lot in terms of systems of equation to find these particular 3. So if b is equal to -1, what is a going to be equal to? So we'll go back up into here. A has to be 3. And if a is equal to 3, what does c, and you use that in terms of the first one, what does c have to be? 1. How wonderful is that? Doesn't get much better than that, guys, so you're ready to be excited. Okay, at least be happy it was easy. All right, so you're going to take a look then at writing this particular equation with those, or this particular integrand with those numerators. So your first integral has a, and a was 3, right? Over x. Your second integral had b on top. What was b? -1 over the x squared. And your third integral had what on the top? 1 for c. And it was over x plus 1. All right, I'm going to do one rewrite of this. This is 3 times 1 over x dx. You don't have to do this rewrite, but just in case anybody needs to see it, -1 times the integral of x to the -2 dx plus the integral of 1 over x plus 1 dx. All right, so what's the integral of 1 over x? Natural log the absolute value of x. Good. And I've got this -1. What's the integral of x squared, x to the -2? What is it? Somebody was telling me.
-1/3 x to the -3.
Not quite.
When you add 1.
Yeah, we got to add 1. It's negative x to the -1, isn't it? So if we add -2 plus 1, we get -1, and then we divide by -1, or in this case I wrote it, it's multiplication, but it's a -1, so it doesn't matter. So we've got this. What's the integral of 1 over x plus 1? It's the natural log of absolute value of x plus 1. Technically there's a u substitution there, but it is highly uninteresting, because if u is equal to x plus 1, the denominator, then du is equal to 1. So it still ends up actually giving us the natural log of that same denominator because there isn't a coefficient on x. Of course, we need a plus c, right? What can we simplify? The two natural logs. I can't simplify the natural logs quite yet. That is, they're added together, but what's wrong with them? Why can't I simplify them right now? One has a 3 in the front. So how can I take that 3 and not have it in the front any longer? I can make it x cubed. So this is the natural log of the absolute value of x cubed. While we're at it, I'm going to just say that this is then plus 1 over x in the middle, and then plus the natural log of the absolute value of x plus 1. And then I can combine these two natural logs together with what operation? Multiplication. And it's the multiplication of what's inside, not the multiplication of the logs. The logs are added. But I can actually multiply then the x cubed times x plus 1. I still have my plus 1 over x. There's nothing I can do about that. And then plus my c. You could multiply the x cubed times the x plus 1. It would actually then turn into the exact denominator you had originally if you really wanted to, but there's no need to. It's perfectly fine to leave it there. Any questions on that?
Is changing the 3 to the x cubed, is that just a property of the?
Yes, there's a log property. Yeah, there's not any calculus there. That's a property of logs. Like think about what would happen if I had log x plus log x plus log x. That would be log of, 3 logs of x. And if I applied the fact that I could multiply them together, I'd have x cubed. So it's a property of the logs, kind of a repeated addition property of logs. Yeah. Any question on this one? Do we have one more example? All right, so on this one I have x squared minus x plus 9 over x squared plus 9 quantity squared. So what do you see on this one? Do I need long division? I actually don't, because if I really multiply that denominator out, I'd have a power of 4 in that denominator, right? So I don't really need long division. But I do have that denominator that I'm supposed to factor, except that x squared plus 9 doesn't factor, correct? And that's a sum of squares. There isn't a sum of squares formula. Difference of squares would be fine, but there isn't a sum of squares. However, I do have that denominator in a factored form already because it's self-squared. So this is kind of like on this one over here when I got to the last problem where I got to this denominator where it had the x squared in it and I said I need to write the x and I need to write the x squared as an option. That's what I'm going to start with on this one as well. So on this one, when I'm doing the writing the two different pieces out, one of the pieces is x squared plus 9. The other piece is x squared plus 9 quantity squared. It's the whole denominator originally. Because those are the two denominators that we could have that then add back together when we multiply to get a common denominator, give me the same common denominator I just started with. Okay. Here's where the other piece of information that I took out of the situation a minute ago comes into play. That denominator on the first one is a denominator with an exponent of 2, right? Degree of 2. So the numerator has to have a degree of 1. So this is the ax plus b I was telling you about before. And we do need it here. I don't have a linear factor like on that last one where I had going on. And here's the nice feature again about this. Because that second denominator is simply a multiple of the first one, it's just an exponent on that same first one, I don't need a degree of the first one to be a degree of 3. Because really that denominator, that second denominator has a degree of 2. Everybody understands that, right? That second denominator really has a degree of 2 squared, so it's a degree of 4 in that second denominator. So technically I should be looking for a degree of 3 in the numerator. But because it's simply a multiple of the first denominator, I'm allowed to simply use the same linear characterization that I had on this one. So I can do cx plus d because it's just a duplicate of what I had before. For the same reason on the last one that I went backwards and I said, wait a minute, we could have just used b only because it's just a duplicate of that other denominator. And that's really helpful, and here's why. If I had to use a degree of 3 on that last denominator, do you know what I would have had to write out? What would a general polynomial of degree 3 look like? Taylor's smiling. Do you know what it would be, Taylor?
Have like 6 terms.
It would have quite a few terms. I'm not sure about 6, but it would have quite a few. It would have cx cubed. It would have dx squared. It would have ex, and it would have f. Do you want all of those on the top of that second fraction? It would work. But I don't want to work with it. I do not want to work with it. And it would be messy and it would be quite complicated in terms of systems of equations. So that's the benefit of the fact that we actually have a duplicate factor here. All right, so what am I supposed to do now? I've got this ax plus b, I've got this cx plus d, and what do I do next?
The top is equal to then x squared minus x plus 9 and figure out what a, b, c, d are.
Okay, so what I'm going to do then, is, Janet, is I'm going to have to multiply them back together, right? so that I can sort of look and see what values the a, the b, the c, and the d actually equal. So my denominator is x squared plus 9 quantity squared. That first fraction does not quite have that denominator, does it? It needs another x squared plus 9 to be multiplied by it. Is everybody with me on that? That's going to give me that current denominator I want, right? So I need to multiply ax plus b times x squared plus 9. So somebody multiply that out for me. What are you going to get? 9ax, okay. Then what? bx squared plus 9b. Perfect. Good job. So that one wasn't especially friendly. However, the next one's quite friendly. Why? Yeah, I already have that denominator, so I don't have to do anything for the next piece. It's just cx plus d. And all of this is supposed to equal my original fraction, like Janet said, which is x squared minus x plus 9 over the x squared plus 9 quantity squared. All right, so we're going to identify powers and things like that. The first one is that I have cubes in this one. So on the left-hand side, what do I have that's cubed? A only, correct? What do I have on the right-hand side? I don't have anything, do I? So what is it? How many x cubes do I have on the right-hand side? I have 0 of them. Well, that's really nice. A is 0. I like getting values of 0. They are really, really nice to work with. All right, let's do x squared next. How about squares? How many squareds do I have on the left? Just one, b. Okay, well that's good, b. And how about on the right? I just have the x squared, which is a coefficient of 1. So now b is 1. This is really nice. Wow, you guys, I'm telling you what. How about x? What pieces do you see? 9a plus c. And what's it supposed to equal? -1. But what do you notice? A is 0. So what is this actually telling me? C is -1. Problem doesn't get much friendlier. We're almost done. My numbers here at the bottom, my constant. What's on the left that's a constant? D. And what's the right that's a constant? 9. So there's really not a lot to do to solve this one, is there? Not for this piece of it, the A, B, C, and D. Okay, fabulous. So we're going to take our integrand and we're going to write it all out again. So I've got an integral. It's supposed to be ax plus b, but a is 0. So what is that numerator of that first value really going to just be? It's just 1. So this is 1 over x squared plus 9.
Do we do anything with the 9b?
Oh, nobody mentioned that one. We did overlook that one. I did too. There were actually 2 constant terms, weren't there? Maybe you guys said it and I missed it. Let's go back and catch that. Thank you, Erica. This is 9b and d both equal 9. Oops, missed it. That's okay, we'll fix it now. You know, b is 1, right? Oh, but this is even better. So what's d? So if b is 1, this is all equal to 9, this means then that d is 0. Okay, I'm happy enough with that. How about you? Get some zeros involved. Okay. All right, so second fraction then is supposed to be x squared plus 9 on bottom, squared. And it's supposed to be cx plus d on top. But d is 0. What was c? -1. So this is negative x on top. -1x if you prefer. Okay. Is everybody good to this point? Because that was all college algebra concepts. So now we're going to do the calculus. Okay, great. All right, so we've got the integral of 1 over x squared plus 9. Do you remember that one? Feels like ages ago we did it. It was quite a while ago. That's arctangent. Jordan got it. This is arctangent. Arctangent with the A is equal to 3. So we're pulling back, like, that's like the second week of class where we did stuff with arc sine, arc cosine, and arctangent. Do you remember that? Yeah. So it's coming back into play again. So this is the A is 3. So what's the antiderivative if we're doing the arctangent? I'll separate this into 2 integrals. If we're doing the arctangent here, I know I've got arctangent. Do I need something in front? Do I need something afterwards? What's going on in my problem?
Is 3.
There is A3 in front, but how is it expressed? I think it's 1/3 2 Caesar. Right? And then what goes inside of the arctangent in that formula? X over 3. Very good, Janet. There we go. Everybody good with that? That's the easier of the pieces. The second one's a little bit more difficult. How are we going to take the integral of negative x over x squared plus 9 quantity squared? I'll give you a hint. It's not foiling that denominator out. That is not a helpful step at all in this one. Substitution. U substitution will work. What would my u be? U is the x squared plus 9. Yes, it is. So what is du? 2x. And why is that helpful? It gets rid of the x that's on top. That's why it's helpful. I don't have a 2, so I'm going to have to, take account for that by putting a 1/2 in the problem. And I also didn't get rid of my negative, so let me pull the negative out as well. So this is a negative 1/2 now. The negative coming from the negative on top, the 1/2 coming from the derivative of u. And then this is 1 over u squared du. But really writing it as 1 over u squared is not the most helpful way to write that. What would be more helpful? U to the negative 2. Okay, so part of the problem done. 1/3 arctangent of x thirds minus the 1/2. All right, antiderivative of u to the negative 2. I feel like I already did this once today. What is it? Yep, negative u to the negative 1. I've got a plus c still. All right, and then if I've got 2 negatives there. How would I make that a plus? 1 over 2u. Will that work? Am I done? I need to put that u back in. But other than that, I am, right? I'm done with the doing the antiderivative part of it anyway. All right, so I've got plus 1 over 2 times x squared plus 9. If you want to multiply that 2 through, you can. You don't have to. The beautiful thing at this point is that nothing combines with that arctangent, so you're done. Any questions?